The Sun, our nearest star, is merely one among roughly 400 billion stars scattered throughout the vast expanse of the Milky Way galaxy. Yet, despite being a solitary beacon amidst countless others, its significance to Earth is unmatched. The Sun not only bathes our world in light, but it is also indispensable to sustaining life and orchestrating vital planetary processes. Its reach stretches far beyond what can be observed with unaided vision. The Sun dictates the global climate, propels winds and oceanic currents, shapes the progression of seasons, and powers photosynthesis, the remarkable mechanism by which plants transform sunlight into nourishment, thereby upholding the entire food web. In the absence of its radiant energy, Earth's atmosphere would dissipate, oceans would solidify into ice, and our planet would be reduced to a desolate, lifeless realm, inhospitable to any known form of existence. Today, in the world of space exploration, we will embark on a journey to uncover how the Sun produces such an extraordinary quantity of energy. What processes unfold within its heart that enable it to shine ceaselessly for billions of years? As the star closest to us, the Sun has always captivated human curiosity. From the earliest skywatchers of ancient civilizations who gazed upon it with their unaided eyes, to the modern spacecraft that scrutinize it from close range, our quest for understanding has never faltered. Thanks to advancements in technology, modern telescopes, orbiting satellites, and powerful computer models, scientists have been able to probe its mysteries with remarkable accuracy. While numerous questions remain unresolved, we have already acquired profound insights into its operation and the immense forces that rule its internal structure. Before we delve into its innermost layers, we must first become acquainted with the Sun's external architecture. The Sun consists of 6 distinct strata. Its 3 outermost layers, the corona, the chromosphere, and the photosphere, form the visible atmosphere. Beneath these lie the convective zone, the radiative zone, and at the very center, the core, where all of the Sun's energy is forged. Our exploration commences with the corona, the Sun's most distant layer. This ethereal envelope stretches approximately 8 million kilometers, or 5 million miles, above the solar surface, and is almost imperceptible to the naked eye. Scientists observe it by utilizing X-ray imaging, or during total solar eclipses, when the moon's shadow unveils a shimmering halo encircling the star. Curiously, the corona is vastly hotter than the Sun's surface, with temperatures soaring up to 2 million degrees Celsius, or 3.6 million degrees Fahrenheit, roughly 360 times the heat of the photosphere. This phenomenon continues to baffle experts, for, in theory, temperatures ought to diminish the further one moves from a source of heat. The prevailing theories propose that the Sun's magnetic field is somehow responsible for this dramatic rise in temperature. Venturing slightly inward, we encounter the chromosphere, positioned just beneath the corona and above the photosphere. This segment is about 2,000 kilometers, or 1,240 miles, thick, distinguished by explosive jets of superheated gas called spicules, which look like a flaming woodland. These spicules can surge upward anywhere from 3,000 to 8,000 kilometers, or 1,860 to 4,970 miles, before quickly fading away within a matter of minutes. The chromosphere also stands out for its reddish appearance, a result of hydrogen gas radiating light at sweltering temperatures. Temperatures here begin near 3,700 degrees Celsius, or 6,700 degrees Fahrenheit, gradually climbing as they near the corona. We now arrive at the photosphere, the Sun's lowest atmospheric layer, and the only one visible from Earth. Its name, borrowed from ancient Greek, translates to sphere of light, since it is the region from which the bulk of the Sun's energy escapes. Light generated here takes about 8 minutes to reach our world. The temperature of the photosphere hovers close to 5,500 degrees Celsius, or 9,932 degrees Fahrenheit, and its surface is mottled. Small features, known as solar granules, emerge as heat bubbles up from the deeper solar interior. Moreover, when the sun's magnetic field grows stronger, dark and cooler patches known as sunspots make their appearance. Tracking the movement of these sunspots across the sun's face led astronomers to the discovery that our star spins around its own axis. Yet, what we see as the sun's surface, the photosphere, is not solid. Instead, it is a glowing sea of plasma about 482 kilometers, or 300 miles, in depth. Should anyone fall into this blistering layer, it would not be a matter of sinking. They would be vaporized in an instant, never given the chance to descend at all. Let us now venture deeper into the sun's internal layers, where the journey of energy unfolds long before it emerges at the surface. Nestled right below the photosphere lies the convective zone. Here, heat is transferred by convection, much like the bubbling motion in a pot of boiling water. In this turbulent layer, hot plasma rises upward in massive bubbles, cools as it nears the surface, and then sinks down again, setting up an unending circulation. Temperatures in this region can soar to as much as 2 million degrees Celsius or 3,600,000 degrees Fahrenheit, especially in its lowest depths. As we have discussed, the further you descend into the sun, the higher the temperature climbs. Beneath the convective zone, we encounter the radiative zone, a region where energy from the core travels outward as light, carried by photons. In this extremely dense layer, photons struggle to escape, bouncing countless times before breaking free. To grasp the scale, a single photon can require more than 100,000 years just to traverse this region and finally reach the surface. Yet, once a photon escapes into space, light covers the 150 million kilometers, or 93 million miles, to reach Earth in merely 8 minutes. At last, we reach the very core of the sun, the origin of its incredible power. It is here that nuclear fusion takes place, with temperatures soaring beyond 15 million degrees Celsius, or 27 million degrees Fahrenheit. Hydrogen atoms smash together, forming helium and releasing vast amounts of energy. This process, called nuclear fusion, fuels all the warmth and brightness that sustain life on our planet. The might of the sun's core is almost unimaginable. Every single second, it unleashes more energy than 1 billion atomic bombs. If a person could somehow reach this core, escape would be impossible. It would take hundreds of thousands of years to get out. Our voyage through the sun's fiery interior draws to a close, but the mysteries of this immense blazing sphere continue to puzzle scientists. Despite remarkable progress and a wealth of discoveries, much remains unknown about its inner workings, lifespan, and the extreme phenomena erupting in its atmosphere and core. Each new mission into space, every careful observation, and every advanced simulation brings us closer to understanding this powerful star that shapes our world. Yet, exploring the sun is not just about unraveling the secrets of our own star. By studying its layers and inner workings, we also gain clues about countless other stars scattered across the universe, helping us understand everything from how galaxies form to the ultimate destiny of the cosmos. If you found this video engaging, please show your support with a like. That means a great deal. And if you have not subscribed yet, go ahead and hit the subscribe button below. Thank you for watching, and until our next adventure.